Black holes are at the center of galaxies, and those are typically gargantuan black holes, millions or billions of times the mass of the Sun. Throughout the years, physicists have depended on a combination of theories such as general relativity, quantum mechanics, and the Standard Model to unlock the secrets of our universe. These theories have effectively explained cosmic phenomena, shedding light on how celestial bodies behave and the intricate nature of particles at the smallest scales. Without theories guiding us, there would be so many questions out there in the cosmos that would go unanswered. But what if we've been mistaken this entire time? Brian Greene has finally broken his silence and said that all modern theories are wrong and that we're living inside a black hole. Join us as we decipher what Brian Greene was talking about 0.4 billion years ago, rotating around each other, going near the speed of light, slamming into each other, creating a tidal wave in the fabric of space, and how this discovery can possibly change everything we've ever known about our reality. In the realm of theoretical physics, few voices carry as much weight as that of Brian Greene. No one can deny his exceptional contributions to the field, particularly in the realm of string theory. His depth of knowledge, clarity of thought, and ability to communicate intricate concepts to both experts and the general public have established him as a leading authority in the scientific community. Greene's expertise extends far beyond his remarkable research achievements. He has an extraordinary talent for unraveling the mysteries of the universe through his books, lectures, and media appearances. Through his best-selling works like The Elegant Universe and The Fabric of the Cosmos, he has successfully bridged the gap between the esoteric world of theoretical physics and the curiosity of the wider public. His unique ability to distill complex ideas into accessible narratives for everyone has empowered countless people to engage with profound scientific concepts. So, in a way, he's also been responsible for growing the scientific community as a whole. But it's Greene's academic background and professional accomplishments that solidify his influential position. As a professor of physics and mathematics at Columbia University, he has mentored and inspired numerous aspiring physicists, fostering a new generation of scientific thinkers. His research contributions in string theory, a framework aiming to unify the fundamental forces of nature, have propelled the field forward and have earned him widespread recognition from peers and experts worldwide. So when a man like this says something, the world listens. And well, he's now said that all of the modern theories we had always looked to for answers are all wrong. We're not just inside our solar system, we're inside a black hole. Everything we've known about our reality is false, and this entire time we've been inside a black hole ourselves. But how could that be? Could modern theories be this wrong? The concept that our universe may exist inside a black hole has actually been explored by scientists for a while now. Over the years, several theories and ideas have emerged to propose how our universe could be connected to or originated from black holes. One idea put forth by some physicists is that every black hole could potentially give rise to a new universe. This notion is based on the concept of torsion, which suggests that inside every black hole, a new universe is created. According to this perspective, black holes act as cosmic gateways, leading to the birth of new universes inside them. Another idea proposes that our observable universe is inside a black hole, which itself exists as part of a larger parent universe or multiverse. In this viewpoint, black holes serve as gateways to other regions or dimensions of spacetime, encompassing multiple universes or realities. The singularity, the infinitely dense core of a black hole, is also seen as a potential source for the birth of new universes. Some experts suggest that the singularity within each black hole could have given rise to our own universe. This idea draws parallels between the initial state of our universe, commonly referred to as a singularity, and the concept of black hole singularities. Another fascinating theory is that our universe originated from a black hole that resides within another universe. According to this theory, when a black hole forms through the collapse of a dying star, a parallel universe is simultaneously born through a white hole located on the other side of a hypothetical wormhole. This idea connects the formation of black holes to the creation of new universes. But that's not all. Some theories actually propose that our universe could exist inside a higher dimensional black hole. This perspective suggests that our universe began as a singularity, a point of infinite temperature and density, similar to how the scientific community characterizes black holes. The idea suggests that our universe is trapped within the event horizon of a four-dimensional black hole. This would mean that we can't even tell that we're inside a black hole, no matter how hard we try. But you see, this theory does go against everything we know about the way our own universe works, things that we've already studied and proven to modern physics. Modern physics encompasses a range of theories that aim to explain the fundamental nature of the universe, from its largest structures to its smallest constituents. These theories have been developed through rigorous scientific investigations and have provided remarkable insights into the workings of the cosmos. At the heart of modern physics lies the framework of quantum mechanics, which describes the behavior of particles at the atomic and subatomic scales. It introduced a new way away from classical physics, which was based on strict laws and precise measurements. By uncovering the nature of the microscopic world, one of the key concepts in quantum mechanics is wave-particle duality. It reveals that particles, such as electrons or photons, can exhibit both wave-like and particle-like properties. This means that they can behave as discrete particles with well-defined positions and momenta, but they can also exhibit wave-like characteristics, such as interference and diffraction patterns. This duality is captured by the mathematical formulation of quantum mechanics, which uses wave functions to describe the probability distribution of finding a particle in different states. Another remarkable aspect of quantum mechanics is superposition. According to this principle, particles can exist in multiple states simultaneously, a phenomenon not observed in classical physics. For example, an electron can be in a superposition of spin-up and spin-down states, meaning it exists in both states at the same time until a measurement is made, collapsing the wave function into a definite state. Quantum mechanics has revolutionized our understanding of the microscopic world, paving the way for technological advancements such as lasers and nuclear power, which rely on the principles of quantum mechanics. So, if you think about it, quantum mechanics explains the world as we know it, but from a microscopic view, that's the building blocks of life. And ever since their discovery, we have known that everything functions a particular way, the way that's supposed to be the truth. But that's not all. There are lots of different theories that have always explained the way our Earth is and how the world really works. Like general relativity, which describes gravity as the curvature of space-time caused by matter and energy. It provides a mathematical framework to understand the behavior of massive objects, and yes, that includes everything like planets, stars, and galaxies. The theory successfully explains a range of phenomena, including the precession of Mercury's orbit, the gravitational lensing of light, and the expansion of the universe. But even then, general relativity breaks down in extreme conditions, such as at the center of black holes or during the early moments of the Big Bang, calling for a more complete theory of gravity. But the standard model of particle physics takes things one step further. This is a highly successful theory that provides a comprehensive framework for understanding the fundamental particles and forces that make up the universe. It encompasses three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Each of these plays a major part in the way our universe works. The electromagnetic force is responsible for interactions between charged particles, such as electrons and protons. But on the other hand, the weak nuclear force is involved in processes such as radioactive decay and certain types of nuclear reactions. The discovery of the W and Z bosons, carriers of the weak force, has provided strong experimental evidence for the validity of the electroweak theory within the Standard Model. The strong nuclear force is responsible for holding atomic nuclei together. It's responsible for the interactions between quarks, the fundamental particles that make up protons and neutrons, through the exchange of gluons. Quantum chromodynamics, a branch of the Standard Model, describes the behavior of the strong force and has been successfully tested in experiments. So the theories we're talking about here aren't mere theories. They've been proven time and time again to be the real deal. Plus, the Standard Model even predicted the existence of the Higgs boson, a particle associated with the Higgs field. The Higgs field is thought to be the one thing responsible for giving particles their mass through interactions with the field. In 2012, experiments conducted at the Large Hadron Collider confirmed the existence of the Higgs boson, providing even further validation for the Standard Model. But despite its successes, the Standard Model still has its limitations too. One significant limitation is its inability to account for the presence of dark matter and dark energy, which are believed to constitute a significant portion of the universe. Dark matter, a form of matter that does not interact with light or other electromagnetic radiation, is inferred from its gravitational effects on visible matter. Dark energy, on the other hand, is postulated to explain the observed accelerating expansion of the universe. Understanding the nature of dark matter and dark energy remains an active area of research in the world of science and is also one of the fundamental building blocks of black holes too. But that's not where the challenges stop. There's also the problem of trying to unify the gravitational force with the other fundamental forces. The standard model doesn't include a description of gravity, which is instead described by general relativity, a separate theory. So maybe Brian Greene does have a point. You see, his expertise actually lies in exploring the fundamental nature of the universe, seeking a unified theory that encompasses all the forces and particles within a single framework. One of Greene's notable contributions is his work on mirror symmetry, a concept within superstring theory. Mirror symmetry establishes a profound connection between two seemingly distinct Calabi-Yau manifolds, which are higher-dimensional geometrical spaces. This discovery revolutionized the understanding of string theory by revealing unexpected relationships between seemingly different mathematical descriptions of the universe. These little differences give way to Greene's theory too. Maybe the differences, albeit minute in their own way, could add up to us actually finding out that we're not just floating through space. Maybe we have been inside a black hole this entire time. But you see, here's where things get even more interesting. There's a reason why black holes are talked about so much in the world of science. That's because this one subject is something that just gets more and more mysterious as you learn more about it. According to current theories, a black hole is a region in space where the gravitational pull is so immensely strong that nothing, not even light, can escape its grasp. This exceptional characteristic arises from the intense concentration of mass within a compact volume, causing space and time to become totally distorted in its vicinity. The thing is, black holes actually possess astonishing properties that set them apart from any other known objects in the universe. One of their defining features is their extraordinary density. The mass of a black hole is compressed into an incredibly small region, resulting in an immensely powerful gravitational field. This gravitational force is so strong that even particles moving at the speed of light cannot overpower it, leading to the formation of an event horizon, a boundary beyond which nothing can return. But despite their immense gravitational pull, black holes have only three properties: mass, spin, and electric charge. Mass is the primary defining characteristic of a black hole and also what ends up determining its gravitational influence. Spin, which is kind of like an object's rotation, describes the angular momentum of the black hole. Because, as well, these things don't just spin in a simple, straightforward way, they go everything on an angle. That's also one of the reasons why black holes can differ from one another too. The tiniest of differences in their angular momentum and the entire black hole changes. Theoretical physicists have developed several models to describe different types of black holes, but overall, stellar mass black holes are the most common variety. They originate from the gravitational collapse of massive stars at the end of their life cycle. Stellar mass black holes typically range in mass from about 3 times to a few hundred times that of our Sun. Their formation involves a cataclysmic event in which the core of a dying star collapses under its own gravitational force, giving rise to a compact object with an intense gravitational pull. Beyond stellar mass black holes, other types of black holes exist in theory, including supermassive black holes and primordial black holes. Supermassive black holes are believed to reside at the centers of most galaxies, including our own Milky Way. They contain millions or even billions of times the mass of our Sun, yet the exact mechanisms of their formation remain a subject of ongoing research. Primordial black holes, on the other hand, are hypothetical entities that could have formed shortly after the Big Bang. They would have originated from fluctuations in the early universe and could range in mass from tiny to supermassive. But even though the more complicated black holes are a little more difficult to study, it doesn't mean that scientists aren't actively studying every black hole they can possibly find. Astronomers actually employ a variety of methods to detect and study black holes, allowing us to delve deeper into the mysteries of these cosmic entities. One approach involves detecting the gravitational influence exerted by black holes on surrounding matter. Observing the movement of stars and other luminous objects helps astronomers identify regions where the gravitational pull is exceptionally strong. For instance, at the center of our Milky Way galaxy, astronomers have observed stars orbiting a seemingly empty spot, indicating the presence of a supermassive black hole. Another method involves studying the matter that falls into a black hole. As matter spirals toward the black hole, it forms an accretion disk, a disk-shaped structure composed of gas and dust. The intense gravitational forces and friction within the disk generate immense heat, causing it to emit radiation across various wavelengths, including X-rays. This helps astronomers get valuable insights into the characteristics and behavior of the black hole. In some cases, astronomers can even directly detect the bright emissions from the material falling into a black hole. As matter accelerates toward the black hole, it gains incredible velocities, generating intense heat and emitting copious amounts of radiation. This emission can be detected across different wavelengths, from visible light to X-rays, and analyzing this radiation allows scientists to decipher crucial information about the properties and dynamics of black holes. But not all methods of studying black holes are so direct. The motions of nearby stars also offer another means of detecting black holes. Researchers can also study the precise movements of stars in the vicinity of a suspected black hole, and with that information, astronomers can discern irregular patterns or deviations that signify the presence of an extremely massive object. These observations provide valuable clues about the mass and location of the black hole, enhancing our understanding of its gravitational influence. The detection of gravitational waves has opened up a new avenue for studying black holes. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects. When two black holes merge, they emit powerful gravitational waves that can be detected by specialized observatories like the Laser Interferometer Gravitational Wave Observatory, LIGO. These detections provide direct evidence of black hole collisions and offer valuable insights into their properties like their masses and distances. But science has made major moves in the past couple of decades. Today, scientists have developed innovative algorithms to identify active black holes in vast numbers of galaxies. For instance, Australian astronomers have utilized an algorithm called Prospector to model the emissions from galaxies and black holes at different wavelengths. This technique enables them to identify the signatures associated with active black holes, providing a deeper understanding of their prevalence and characteristics in the universe. Once black holes are detected, scientists employ various methods to study them in detail. They observe the motion of stars and gas in the vicinity of the black hole, which provides insights into its mass and gravitational effects on its surroundings. So they can gain valuable information about the physical processes occurring near black holes. Reverberation mapping is another technique used to study black holes. This method involves measuring time differences between emissions from different locations near the black hole. By analyzing these time delays, astronomers can map out the orbits of gas and photons around the black hole, unraveling the dynamics of the accretion disk and the interplay between matter and radiation. But that's not all, though. Cutting-edge experiments such as the Event Horizon Telescope have also revolutionized our ability to study black holes. The EHT is a global network of radio telescopes that work together to create an Earth-sized virtual telescope, enabling scientists to capture images of black holes with a resolution that was unheard of in the past. This was the telescope network that successfully imaged the supermassive black hole at the center of the galaxy M87, providing visual evidence of the event horizon. Even though this was a known fact before too, being able to see what scientists have described for decades is something else entirely. Now that we've actually seen a black hole, you'd think that it's all pretty clear, right? But that's where Brian Greene throws a wrench in all of that logic. His thought-provoking hypothesis proposes that our universe exists within the confines of a black hole. This claim actually stems from the intricate interplay between general relativity, quantum mechanics, and the properties of black holes. According to Greene's reasoning, if we consider the laws of general relativity, particularly Einstein's theory of gravity, and apply them to the vast scale of the cosmos, intriguing possibilities emerge. Black holes, characterized by their intense gravity, can significantly distort space and time in their vicinity. Right inside a black hole's event horizon, where the gravitational forces are the strongest, the fabric of space-time becomes highly curved, leading to some fairly interesting effects. Greene suggests that if our universe were inside a black hole, the gravitational force acting within it would be responsible for the expansion and structure we are able to observe. In this scenario, the universe's expansion could be attributed to the gravitational force exerted by matter falling into the black hole from outside regions. The gravitational collapse of matter could also account for the formation of galaxies, stars, and other celestial structures that we've been studying for decades.